Hi, I'm Ayan Banerjee and I have an optical tweezers lab here in IISER Kolkata. So me and my collaborators are going to talk to you about our recent paper in NJP on the spin-orbit interaction of light in optical tweezers. Optical tweezers employ a tightly focused beam to trap and manipulate microparticles, and this tight focusing leads to the spin-orbit interaction of light, or SOI of light as we call it, which leads to an interdependence of the polarization and trajectory of the propagating light. So what we show in this paper is that the effects of SOI can be enhanced in optical tweezers by using a stratified medium in the path of the trapping beam. The enhanced SOI and associated spin Hall shifts actually cause an increase in the trapping volume and also creates regions of high spin angular momentum density where single microparticles can be trapped and rotated controllably by using just a simple linearly polarized Gaussian beam having no intrinsic angular momentum. The stratified medium is created by using a polymer cover slip that is refractive index mismatched with the microscope objective immersion oil, as we see in this cartoon here.
Hi, I am Nirmalya Ghosh. I have a biooptics and nanophotonics laboratory at IISER Kolkata, and I have helped in developing the theoretical treatment for this paper. To model tight focusing, we used a variant of the Debye-Wolf theory. The details of this theory can be found in our paper. Finally, the intensity at the focal plane can be expressed by this expression where I0, I1 and I2 are the diffraction integrals. One can see that the total intensity depends on the polarization angle psi. This is called the linear diattenuation effect, which is a manifestation of the geometrical phase. Finally, this linear diattenuation is manifested as formation of distinct lobes in the focal plane as shown in this simulation. The other interesting manifestation is the spin Hall effect of light, which arises due to the input polarization dependent longitudinal component of the field, and this leads to generation of extrinsic orbital angular momentum and transversal flow of energy. This eventually leads to generation of regions of opposite circular polarization near the focal plane as shown here. In fact, a particle trapped in this region will start spinning.
Hello, my name is Soumyajit Roy. My laboratory EFAML at IISER Kolkata specializes in the synthesis of soft oxometalates.
The pea-pod-shaped particles used in this study are prepared from a phosphomolybdate kakin-type polyoxometalate precursor and are typically of colloidal length scales.
I am Basudev. I've worked with Dr. Ayan Banerjee and I have been involved in the experimental and the simulation work of this particular paper. This here is the microscope that we've used for the experiment, and the light enters to the back port of the microscope and comes out to the side port and goes into the camera. Part of the light also goes into the quadrant photodiode. Continuing from our simulations, if you have a pea-pod-shaped particle at one of the high spin angular momentum density regions, the particle starts spinning, and we can even change the direction of spin by placing it on the region having opposite sign of the spin angular momentum density. The rotation can also be controlled by having two X-polarized trapping beams focused adjacent to each other, and the spin angular momentum density distribution for the two beams will look like this, with the regions of opposite spin adjacent to each other. If the beams are overlapped, then for equal intensities, the net spin angular momentum density in the overlapping region is 0. Thus, turning on the second beam stops rotation. However, if you have different intensities, one should be able to change the direction of rotation.
This is the first case where turning on the second beam stops the rotation, and this is the second case where turning on the second beam reverses the direction of rotation. To summarize, SOI in optical tweezers is amplified in the presence of a stratified medium. SOI leads to two distinct effects: a spin redirectional geometric phase and a large spin Hall effect, which creates regions of large spin angular momentum density near the focal plane of the optical tweezers. Trapped particles can actually be controllably rotated in those regions. Finally, our experiments are the first instance of using probe particles to actually measure the spin angular momentum density of non-paraxial fields.